So what we're going to do today is something that we have done a handful of times before with other topics, and that is to create a mathematical model that will have a predictive effect about what happens next in a particular phenomena. So we've done this before. For instance, I think most recently with SHM, we developed a time-based formula that would predict where an oscillator would be in the future. And then we were able to manipulate that to work out what speeds it would have and what accelerations it would have and what forces it would have on it. And that allowed us to have a theoretical basis by which we could take control of the phenomena. We could construct it to behave in a way that we wanted it to behave. And that's a theme that runs throughout physics. And I've said to you before that having an A-level in physics is much more than having some physics knowledge. It's about the abilities you have to manipulate data, analyze situations, and make predictions about what will happen next. And those skills are very highly valued in the wider world beyond physics, as well as within physics. The more times that you can be exposed to the mathematical modeling technique, the more likely you are to be able to dust it off and put it to use in your own sphere later on in your life when you come to be doing these things, if you do. So each time we do it, I just kind of modeling, and I just show you how it's done and try to pick out the key points. And really what you're learning is the skill of modeling rather than the outcome of the model. You'll never be examined on this at A-level, so most of the rest of this hour is not going to be something that you'll have to serve up on a test. We don't know what are happening with the exams, but even if the exams were to go ahead, this isn't something that you would have to demonstrate. However, the final equations are something that you need to be able to know and manipulate and apply. So we're going to spend Monday's lesson making sure that we understand the model, but today we're just going to derive it. So we're going to do it twice. We'll start with discharging because it's the first one we did and it's a little bit easier, and then we'll move on to charging after that, and hopefully we will get the whole thing done inside an hour. So let's make a start on how to model a discharging capacitor. Okay, so we obviously need a capacitor, and we're going to assign a variable to it, which is a constant. Its capacitance C. And when it is charged, it will have plus Q charge on one plate and minus Q charge on the other plate. And that will result in the capacitor having a potential difference, V. And when we attach it to a circuit with a resistor in it, that potential difference will cause a current I to flow through the resistor R, and this will result in a time dependence for the amount of charge. The amount of charge, as we saw from the experiment, is going to fall over time. And as the amount of charge falls over time, we would expect the potential difference to fall over time. And as the potential difference falls over time, we would expect the current to fall over time. So we're expecting time-dependent equations that demonstrate a gradual reduction as time goes on for both Q and V and I. To be clear, C and R are constants and will not change during the experiment, but we would expect that both C and R will have an effect on how long it takes to discharge. The bigger C is, the more charge there will be, and the bigger R is, the harder it is for the current to flow. So we would expect that despite being constants, that C and R will turn up in our eventual equation. So in terms of the modeling technique, once you have established the situation, as in the diagram, and once you have established what variables and constants are in play and assigned some letters to them, you then need to start looking at relationships between the variables. So you start searching through your mind for any links that you know, and we have this from this topic, which is that the amount of charge stored on the capacitor is equal to C times V. We also have, from years ago, when we first started looking at circuits, that the potential difference V causing the current I through a resistor R are related by that formula, V equals IR. And you can see immediately that we have the potential to move this V and substitute it into this equation to get Q equals C times I times R. And indeed, we can do that. But the goal here is to find a time-dependent equation, and time isn't currently in here. So we still need to search around our memory for another equation that is involved with at least one of those variables that has a time dependence in it. And if we think not too far, still within the electricity topic, we have this equation that the current is equal to the rate of change of charge, the rate of flow of charge around the circuit. And that gives us our time dependence. And so we can now insert the I here, and we'll have a T in our equations. You know that A-level physics doesn't require A-level maths, and therefore the inclusion of the derivative here might be a little bit confusing to some of you who aren't doing A-level maths, but just remember that it just means a kind of a version of delta Q over delta T, the amount of charge divided by the amount of time. We just allow the time to get very, very small and then consider lots and lots of successive times rather than averaging out over a big long time period. It accounts for the rate of change being non-constant. And we would expect the rate of change to be non-constant. And you demonstrated a non-constant change with your graphs. It wasn't a straight line, it was a curve. And that's because we expect that when the capacitor has a very large amount of charge on it, it pushes off a very large amount of charge in the first second, say, because there is a very large amount of repulsion. But then as the capacitor discharges and there's less and less charge on the capacitor, there'll be less and less repulsion to push the electrons off the capacitor, and therefore we would expect the charge to go down at a slower rate as time goes on, and therefore delta Q over delta T wouldn't be appropriate. We need to think on much smaller time frames and have a non-constant rate of change. And that's where the derivative comes in. You'll notice that highlighted in red is a minus sign, which isn't usually there, but we need to include in this model. And this now brings you on to another fact, that when you start gluing equations together in a model, you just need to be very, very clear that you can straightforwardly just glue the equations together. Now, in this particular case, Q would usually be the charge flowing around the circuit due to a power supply. And it is the amount of charge flowing around the circuit, but we have already accounted for the charge by assigning the variable Q actually to the amount of charge that's sitting on the capacitor. Now, the charge that's sitting on the capacitor is about to be the charge that is flowing around the circuit, and therefore it is appropriate to use the same value Q. But what you have to appreciate is that the current flowing around the circuit is a positive current, from positive to negative, just the way the conventional current flows. It is a positive current. But if we're going to use the variable Q to denote the amount of charge on the capacitor, then the amount of charge on the capacitor is going to decrease as a discharging capacitor, and therefore dq dt is going to be a negative number. But we need it to be a positive number if we're going to double it up to represent the charge flowing around the circuit as the current. So we just need to insert a minus sign there, so that when the minus sign meets the negative derivative, the minus minus will become a plus, and we will end up with a positive current as required. That's a tricky aspect. We can go through it at the end if you want me to, or on Monday's lesson, which you've had time to have a think about it if you want to. Okay, so as I said, we're going to substitute the I into that equation to eliminate I, and then we're going to substitute V to eliminate V over here. Okay, so just as algebra in your notes. By the way, this PowerPoint's already on Classroom, so I should have said at the beginning, you don't need to be scribbling like crazy. You will have time to add to your notes later if you need to. You can go back through the PowerPoint and watch it again. Okay, so that's what we're going to get. We're just going to rearrange the equation to get the derivative as the subject. Okay, so what we've got here is a first derivative. It's equal to a negative constant, 1 over CR, and then multiplied by Q. We have met this kind of modeling before, in which the it's called an equation of motion, even though nothing is actually moving. This equation is our fundamental aspect to our model now. We've glued together all the bits and bobs that we know about capacitance and what's going on. And this equation is the fundamental aspect of our model for capacitance now. However, it's not very useful because it's in the form of a derivative, and most of the time we don't really care what the derivative is. What we want to know is what is Q as a function of t. So I've noted over here that Q is a function of t, but rather than having dq dt equals something to do with q's, what we really want is Q of t equals something to do with t's. So we're going to have to solve this differential equation. Just a note, for the mathematicians and for those of you that go on to do science or engineering in the future and might end up solving equations like this, as we've said before, this is known as a first order differential equation because its highest order derivative is 1. It's a first derivative in Q. And it's an ordinary differential equation. That means that we've only differentiated with respect to one variable, in this case, time. Note the form of the equation. On the left-hand side is the derivative, and on the right-hand side is the original function. So this formula is very, very similar to dq dt equals q. There is a multiplicative constant at the front, which we will need to sort out. But in form, this is differentiate something, it turns into itself. Now, the mathematicians will already know what the solution to this is, but as we did with sine and cos, I just want you to see where it comes from. So the solution is known as the exponential function. And just like the sine and cos functions, when we were doing SHM, it is constructed to be the solution to this equation. So a mathematician has sat down and they have constructed this infinite sequence in polynomials, and they have understood that when you differentiate these terms, they turn back into themselves. It's an infinite series, and so we get to play the game of infinity minus 1 is still the same size as infinity. So when we differentiate the 1, it goes away. Differentiate the t, it becomes the 1. Differentiate t squared over 2, and it becomes the t. Differentiate t cubed over 6, and it becomes t squared over 2. And so you can see that the derivative is equal to the original function, albeit one term less, but that's okay because infinity minus 1 is still infinity. Just like with sine and cos, we construct this function in order to be the solution to our exponential, to our differential equation, that first derivative equals original function. But then we also recognize it for an existing function that we have already studied. So if you raise the number 2.718 to the power t, it produces this function. And this number, 2.718, it's an infinite fraction, an infinite decimal, has been identified as a really cool number. It's what you get if you set t equal to 1 in this equation, e to the power 1. So 1 plus 1 is 2, plus a half, plus a sixth. And if you keep adding on the fractions, it turns into 2.718. and this number is known as E, Euler's function, or Euler's number. Now, just like with sine and cos, once we recognized our solution for being something that already had a name, this thing can be called exp of t, the exponential function, but it already has a name. It's e to the power of t, and so we might as well call it for what it is. So this is the solution to our equation, except we haven't dealt with the multiplicative constant, and we need to do that using the chain rule. So we just need to do a variable substitution. We need to substitute, instead of having just t all on its own, we need t multiplied by our constant. And then when we do our differentiation, we'll differentiate with respect to the substituted variable, and then multiply by the substitution differentiated with respect to time, which will just be minus 1 over CR. And again, for the mathematicians, later on, I would suggest, if you can't see it already, that you just differentiate that function in front of you and establish to yourself that it still turns into the into itself, but this time multiplied by minus 1 over CR. For the non-mathematicians, just keep going blah, blah, blah to yourself for a moment longer. I mentioned when we were looking for solutions to the differential equation in simple harmonic motion that there is a fundamental theorem in calculus, which is the study of differentiation and integration. And this theorem states that, and has been proven to show, that you have completely solved your differential equation if your differential equation has an arbitrary integration constant in it, the same number of constants as the order of the equation. So as is a first order differential equation, so we're seeking one arbitrary integration constant. And at the moment we don't have one, except we kind of do, because there's a 1 at the front of here. And again, you can prove to yourself later if you need to, that if you multiply this through by an arbitrary constant a, then the a will come out of the derivative when you differentiate it, and then you can factor it back in afterwards, and therefore multiplying through by a constant at the front doesn't alter this from being a solution. And now we have one arbitrary integration constant, which means that our solution is complete by this theorem of calculus. Okay, so this is our solution, a constant multiplied by e to the power of minus t over CR. As noted, when you drew your graphs, this is mathematically an exponential decay. It's an exponential function because it's got e to the power of something in it. And it's a decay because of this minus sign here, which means that as t gets bigger and bigger and bigger, e to the minus t gets smaller and smaller and smaller. And I'll show you a graph of that in a minute, but it looks just like the one you drew. As expected, the constants c and r are in the formula, which is what we were expecting. And then rather than write this multiplicative constant as an a, we can give it a name that will seek to remind us what it is. And so you will remember that anything to the power 0 is 1. And so when the time is 0, e to the power of 0 will return a 1 for all of this bit. And therefore the multiplicative constant at the beginning is actually the value of the charge when time is 0. So writing it as q subscript 0 just reminds us that the constant is the initial value of the charge stored. This is then a number that starts at 1 when t is 0 and gets smaller and smaller and smaller and tends to 0 as time goes on. And therefore, this is basically nibbling away at this number. It begins as 1 times this number, and then as time goes on, this will always be a decimal 0 point something that reduces this down ever closer to 0. We can now derive our other equations as we discussed in class the other day when we were doing the graphs. V is just equal to Q divided by C. So if we just divide both sides of this equation by C, this side turns into V, and this side turns into Q0 over C. So the original charge divided by the capacitance will just equate to the original potential difference. And again, we can see that by setting t equal to 0, that becomes 1, and we've got that the value of V at time 0 is V0. So this is the initial PD. And then to obtain the current, we note that current is just V divided by R. And so if we divide both sides of this equation by R, we end up with I on the left and V0 over R on the right, which is just the original current, the initial current, which again you can see by setting t equal to 0 here. And when you do set t equal to 0 here, this becomes 1, and again I of 0 is I0. To summarize then, when we have this circuit arrangement, which is a capacitor discharging through a resistor, we would expect that over time, the potential difference will decrease from an initial value exponentially. The charge will decrease from an initial value exponentially. And the current will decrease from an initial value exponentially. As graphs, all three of these graphs take the same form, and they all look like that, where this value at the top is either V0 or Q0 or I0. Everything that I have said so far up until this slide is non-examinable, but this slide is. You do need to know those three equations. They're printed in a fashion on your formula sheet, so you don't need to memorize them, but they're not printed as explicitly as that list. So you do need to have a familiarity with them in addition to the formula sheet. I'll show you the formula sheet at the end. And you do need to know the shape of the graph and be able to sketch it if asked to do so. As exponential functions, however, they all share a key characteristic involving the rate of change. So that's what we're going to go on to next. And this is that if you want to be clear that a function is exponential, they all share the same characteristic that in equal amounts of time, they all reduce by the same fraction of their value. And we discussed this in class last lesson. So if we're going to test this, we need to take fractions of the value, and we might as well halve it because we can do that in our head and it's nice and simple. And we should be familiar with this from our study of GCSE radioactivity as well. And indeed, we'll come back to this when we do radioactivity at A-level as well. So let's just consider that we start the stopwatch when the initial value of the potential difference is V0, and we wait until the value becomes V0 over 2. So we keep an eye on the voltmeter, and if it had begun at 6 volts, we just keep watching the voltmeter until it gets down to 3 volts. Or on the graph, if we know it starts at 6, we halve it down to 3. When that takes place, the time on the stopwatch will be the time it took to reach half of its value. So let's give the variable t a specific value, which we'll call t with a subscript half. And you might remember from radioactivity that we refer to this as the half-life. So what it comes down to now is solving this equation. The V0, the E, the C, and the R are all just numbers. The only bit in there that's unknown to us is t half, so we need to solve this equation. And this is the first time at A-level where if you haven't taken A-level maths, you are literally at a disadvantage rather than kind of feeling at a disadvantage. You really are. because all of the calculus stuff is not examinable, but the exponential function is, and it is part of the Maths A level, and you won't have studied it. So we're just going to take this in little baby steps for those of you that are less familiar. And my suggestion to you in solving this equation, even for the A-level mathematicians, is that you are much less likely to make mistakes if you restrict yourself as far as possible to the maths that you are most familiar with. And you have been rearranging equations algebraically since year 6, but you've only been using the exponential function this year. So I would do as much using algebra as I could if I were you before I start playing with any fancy A-level mathematics. So first things first, you can cancel the v zeros from each side of that equation. And then you note that something to a negative index is just 1 over it to a positive index. So in actual fact, this side of the equation is just 1 over e to the plus t half over cr. So you've got 1 over 2 equals 1 over e to the power of something. And therefore, if the top's the same, the bottom must be the same. And therefore, we can write this, that the 2 that's in the denominator here must be equal to the e to the plus t over cr, which is in the denominator here. This minus sign means 1 over. And now you need your A-level mathematics. So you know that the inverse function of multiplication is divide, the inverse function of addition is subtraction. Well, the inverse function of raising e to the power of something is known as the logarithm function. So if we apply the logarithm function to both sides of this equation, we get the logarithm of 2, which your calculator will provide for you. You have a button on your calculator that applies the logarithm function to numbers. So your calculator will tell you what the left-hand side is. On the right-hand side, if you apply the logarithm function to the exponential function, because it's its inverse, they kind of cancel each other out, they go away, and you're just left with the t half over cr. For the non-mathematicians in the room, the ones who aren't doing A-level maths, you need to remember that step, that you take what is called the logarithm of both sides of the equation, and the e goes away. You're going to need to let me know if you want me to go over that, those of you that don't do A-level maths. There'll be time on Monday if you do. Please note that the logarithm function can be written in different ways. The most general format of it is written log, L-O-G, but this isn't the most general form of it. This is a particular logarithm that is the inverse of the exponential function as opposed to any other numbers raised to a power. So this is known as the natural logarithm because e is in this hallowed place in the functions of raising things to an index. And so this has been given the term natural logarithm. And so rather than write log, we write ln, the natural logarithm. Just a heads up, I have had students regularly over the years who have got very confused in the stress of an exam situation, or even just the confusion of lots and lots of maths being thrown at them all at the same time, who have read that as 1 Newton, and it's crossed their mind slightly why the Newton is in lowercase. But you can see that in some font faces, the lowercase l does look like a 1. So just be aware, if you're dealing with exponentials, it's going to be a logarithm, not 1 Newton with a lowercase n. Sounds silly when I say it in the middle of a lesson, but honestly, it comes up again and again, people making that mistake. Okay, so just rearrange because it's t that we want. And this is our prediction. And we should now be able to test this. So I'll stop talking for 60 seconds and you can whip out your calculator. If you remember, the capacitance that we used in class was 4,700 microfarads. and the resistance was 22 kilo ohms. So if you just multiply 4,700 times 10 to the minus 6 by 22 times 10 to the 3, and then find the log button on your calculator and multiply that by log 2, which is about 0.693, then you should be able to predict the half-life. You should be able to predict how long it takes for the value of the capacitor to halve. And then you should be able to consult your graph that you drew last lesson and see if that matches up. So I'm going to give you 60 seconds to do that. 4,700 times 10 to the minus 6 and 22 times 10 to the 3. Okay, so hopefully you came up with 72 seconds, and hopefully you've just had a very quick glance at your graph and checked that it did take 72 seconds to go to around about 3 volts. But more than that, it's now going to go 72 seconds to keep halving. So to get down to the 3 volts will have taken 72 seconds originally, but then to halve to 1.5 volts, it will have taken another 72 seconds. And then to come down to 3/4 of a volt should have taken another 72 seconds. And you should be able to read that data from the graph, and that, beyond anything else, is your evidence that the curve that you drew is not just some random curve, but is in particular an exponential curve. And in particular of that, an exponential decay curve, because it is getting smaller and smaller and smaller. And if ever asked to prove that your data represents an exponential decay, this is what you do. Horizontal and vertical dashed lines indicating a constant time step on the x-axis. Okay, all of this is great, and you might expect that I would stop talking there, but you haven't factored in the mindset of the electrical engineer. You see, an electrical engineer doesn't need to halve things in their head because they use computers all day long, and they have computers that do this for them, even if that computer is as simple as a calculator. And they are mathematically very adept, and they find the log 2 factor an ugly inclusion. Why should we have C times R times this log 2? Why should we have a 0.63 on the end of it? It's ugly and it shouldn't be there. And the only reason it is because somebody decided to halve something. The halving resulted in a log 2. And that's just offensive to a pure mathematician or to an electrical engineer. Why pander to the human need to do things simply when mathematically there is a much purer way of doing it? So, says the electrical engineer, why should we halve things when we can ETH things? Obviously. So if we just repeat all of that all over again, you'll note that if we choose to take an ETH at 2.718 instead of a half, then when we do our analysis and we get to this stage and we apply the logarithm to both sides of the equation, well, you can try it yourself on your calculator, but log E is just 1, which means there is no log 2 factor, no 0.693, there's just the purity of 1, which means that we end up with a different measure of the time it takes for the capacitance values to decay. Instead of referring to the half-life, we're now going to refer to the ETH life, which does sound a little bit silly. So we're going to give it a different name. We're going to call it the time constant. The time constant is equal to CR, and it does determine how quickly the capacitance decays. So it's still a time in seconds, but this time without the 0.63693 factor. So it's just 103.4 seconds. And again, you can read that off your graph as well. It's just that you need to not halve the values, you need to ETH the values. So divide your 6 by 2.718, and that should give you a time value of 103 seconds. And then if you keep doing it, you should find that again, it ETHs in equal time periods. This is known as the time constant. So a departure from the half-life. Now, when we get to radioactivity, just don't be confused. We're going to stick with half-life for radioactivity, largely because if a nuclear physicist screws up, they kill rather a large number of people in a nuclear explosion. Whereas if an electrical engineer screws up, they tend to just mean that your washing machine cycle finishes a little bit earlier than it should have done. So generally, the stakes are a lot lower in electrical engineering in terms of how many people can I kill today. So the nuclear physicists have never transitioned to an ETH life because they really do want to be able to check things in their head and make sure that everything's okay. Whereas the electrical engineers continue to rely on their computers. Okay, that's discharging a capacitor in its entirety now. 3 equations, a graph, and a time constant. I'm just going to pause here and ask any of you to ask me any questions if you have them. Okay, you might find that you've got some questions by Monday because you'll have had time to reflect on it by then. As I said, though, none of this is actually examinable apart from the conclusions. Okay, let's repeat the whole thing again, but a little bit more quickly for charging a capacitor. So similarly, we need a capacitor of capacitance C, and this time we're going to connect it to the circuit with a resistor in it, but now there's going to be a power supply as well. So that we don't get muddled up between our V's, let's denote the potential difference of the power supply by the EMF symbol, epsilon, and that's a constant. And we'll stick with R for our resistance. When we do attach the power supply to the capacitor through the resistor, it will charge using a current I, resulting in plus Q and minus Q on the plates of the capacitor, and a potential difference V. Again, we now need to ask, what formulae do we know that relate these variables together? And we still have this one. And we would like to be able to write V equals IR again, but this is the V of the capacitor, not the V on the R. The V on the R is the epsilon take away this V. So we just need to be clear that when we relate the current to the resistance, it's this potential difference we use, not this one. And that's why we've got epsilon minus V rather than V there. So that's a slight difference. You can also come at that from Kirchhoff's second law, that this is technically, once it's charged a little bit, a second source of EMF in the circuit. This is a closed loop, and so we need to sum these two EMFs to get the overall EMF of the circuit. Because this is the positive plate and this is the positive plate, they're aligned oppositely to each other, which is why one subtracts from the other. And if we use the big number, take away the little number, that'll mean that our current is positive. On the subject of currents, that again is the rate of change of charge, but this time the charge on the capacitor is increasing because it's charging, not decreasing, and therefore the derivative is naturally positive, and therefore we don't need to worry about a corrective minus sign here to make the current positive. As before, we can now start substituting. We can eliminate R, and when we could rearrange this and throw it into here, But just for some variety, so that we don't get very bored, let's do it a different way to how we did it last time. And instead, let's substitute the charge instead. I know, it's very exciting leading such variety in our lives. Okay, so here we go. Eliminating I and eliminating Q and rearranging to get ourselves the derivative as the subject. Very similar equation to last time, except from not the same as the original function, easily fixed. However, the tricks for solving, we're just going to do a substitution. So instead of using this in brackets, we're just going to use the bracket as a single variable, and we're going to call it x. And now we've changed our v into an x, so we're going to need to do something similar over here. So if we just differentiate the bracket with respect to t, the epsilon bit's a constant and goes away. And so we actually find that dx dt is just minus dv dt. So we can sub this out for minus dx dt, bring the minus sign onto this side, multiply through by the constant, and look at that piece of wonderfulness. We have the original equation that we just solved for discharging a capacitor. So we know that this is discharging a capacitor, and now all we need to do is swap the x back into these. So the x here is just this bracket, so that's easily enough. The x0 here is the value of x at time t0, which is the value of epsilon minus v at time t0. Epsilon's a constant, and v at time t0 is just what we're calling v0. And therefore, v0 would be expected to turn up here, but it isn't, because remember, this is a charging circuit, and at the beginning, the capacitor doesn't have any charge, and therefore doesn't have a potential difference, and v0 is 0. Just going to collect this together so that it says v equals as opposed to epsilon minus v. So if we just do that, bring the epsilon to the other side and factorize it, we've got one lot of epsilon plus epsilon times this e term. So this is our charging equation for v. It looks a lot like the discharging equation in that it still has this factor in it, but now it's 1 minus this factor. So remember, this is a term that begins at 1 and tends towards 0, and therefore 1 minus it is going to start at 0 and tend towards 1. And then if we multiply by this, this becomes the value that v is tending towards. And so actually it reinforces what we were expecting, that epsilon is actually the final potential difference. Okay, so if we just summarize that as we summarize discharging, when this is our circuit arrangement, we end up with the prediction from our model that the potential difference will grow towards E, epsilon, the EMF, exponentially. And then if we multiply through by C to get the charge, then we end up with the EMF multiplied by C, and that will be the final charge because epsilon is the final PD. And then if we're thinking about the current, it's not as straightforward as just bunging it back into V equals IR, because remember the formula is epsilon minus V equals IR. So you can play with that yourself up here, and the epsilons will cancel. Or you can just differentiate this equation because I is dq dt. Whichever way you want to do it, you end up with a different factor now that the 1 disappears, either because it cancels out when you do epsilon minus V, or because when you differentiate it, this constant term disappears. But either way, notice that we're back to the original form for the current. And again, that's because we do expect the current to begin very, very big when there is no capacitance to affect the V equals IR circuit. If this isn't here, we just have epsilon equals IR, and that's quite a large current. So we expect this to begin large, but then as this PD builds and starts opposing this one, we would expect this current to reduce over time. And so we would expect a decay equation for the current. Graph summary. Blue line is the one we're familiar with. For the current, still as an exponential decay, but now we have an exponential growth formula, which is tending towards the final value, which will be the power supply for the voltage, and it'll just be this QF, this final value of charge, epsilon times C, for the final charge. Summarize everything then. We've got 3 equations for discharging, all of the same form. And we've got 3 equations for charging, of which one is the same form, but the others are now growth formulae that have this 1 minus factor in them, as opposed to just the exponential all on its own. The graphs look like this, and they are determined how quickly they progress along their journey using the time constant, which is just C multiplied by R. This slide is the entirety of the examinable content from today's lesson. That's a lot to remember, and the examiner knows that, so they give you a little helping hand by printing some of it on the formula sheet, but the helping hand isn't quite as straightforward as it could be. All they print is the form of the equations in a generic variable x like this. There is no indication as to what x is, and so you will have to remember that this formula, which is not in blue and demarked particularly from this one in the formula sheet, you'll need to remember to use this formula in 4 of the instances, and you will need to remember which 4 those are. And you'll have to use this formula for the other 2 instances, and you'll have to remember what those 2 instances are. And then just to be extra annoying, we have just discussed that a subscript of 0 is a very good idea for an initial value. And this is the initial V, initial Q, initial I, and all of that's great for this formula. But as we've noted, this is the final PD and the final charge. And I find it really annoying that the examiner is insisting on the symmetry and using a 0 subscript on this formula when it very much should be an F for the final value, not implying an initial value. That's just my own personal annoyance, which I share with you so that you can adopt it also. My suggestion to you would be to spend whatever private study time you're going to spend between now and our next lesson going back through this PowerPoint, finishing off your notes, trying to understand it, but in particular, committing this slide to memory as far as you can. And then I'll devote the entirety of Monday's lesson to you doing some questions while I stay on the meet, and you can interrogate me and ask me any questions you've got about today's lesson. We have got about 5 minutes left now, so if there is anything that you want to stay and ask me, you're welcome to do so. Otherwise, you've probably filled your head with enough for today, and we can call it a day there early if you want to. So it's up to you. You can stay and ask questions, or you can leave.
Thank you.
Thank you, sir. Thank you, sir.
Thank you, sir.
Cheers, sir.